Okay, good afternoon. We are the team has made the cylindrical robot. The team is formed by Martinez Carrillo, Carlos Ignacio, and Muñiz Cortés Ángel Enrique. The history of the project. For a mechatronic engineer, it is of a great importance to understand and know how to analyze any kind of robot. In this case, the project forces us to learn and apply everything seen in class to develop the full functional robot, and of course, improve our problem-solving abilities. For the justification, as a student of mechatronic engineering in the Autonomous University of San Luis Potosí, we have to complete some course to complete recurrent credits. One of that course is Robotics A, the class when we have to do a functional 3 degrees of freedom robot in your credits to prove it is necessary to make a cylindrical robot that can move at least 10 by 10 by 10 centimeters cube and a mass of 100 grams. That robot is the most important project for the class, and it's important that it shows complete improvement and the required positions. For the project scopes, our 3 degrees of freedom cylindrical robot had some sort of scopes designed to meet the requirements of the projects, and these here are listed below. At least 10 by 10 by 10 centimeters volume in the middle of the workspace. It will be able to pick up items or stuff up to 100 grams. It will be made with PLA material and aluminum. It will have an interface where the user should be able to control the robot. And apart from all this, it will have a certain precision and through serial communication. All the data will be processed and sent to the joints to move in a certain way. Project background. A cylindrical robot has a 3 degrees of freedom. It has a rotative joint and 2 prismatic joints. It is called cylindrical because of the workspace it's provided. The base joint is rotational one, a prismatic one oversees the head, and another one oversees lateral scope. Some applications of cylindrical robots include spot welding automation, robotic casting and molding machine handling, general machine handling applications, material handling applications including package assembly and palletizing, robotic coding and finishing applications, automated assembly operations. For this case, the robot is connected to an Arduino, and this one will be communicated with the computer using a USB TTL, and the interface is developed in MATLAB. Mechanical design. For the mechanical design, we use the following materials: PLA, stepper motors, some servo motors, screws, and zoom marbles. The electrical design is the main component we need to calculate are stepper motors, servo motors, and the power source. For the stepper motor, we must know the approximate weight of the x-axis. All the components of the x-axis are listed below, and the total weight are 145 grams. On the internet, we can find a lot of models that we can use for that, but the best option cost benefits is a 12 volt stepper motors. This offer use a 700 gram force each centimeter torque. That's more than enough for a required application. We decided to use the same model for both joints. For the rotational joint in the base of the robot, we need a more powerful motor to guarantee that it can move all the components. We make a zoom with the 145 grams for 2, 45 grams for base, and 15 grams of 10 by 10 by 10 cube. It's equals to 385 grams approximately. Searching on internet, we found a cheap and powerful servo motors. And all these components plus the stepper motors, drivers, and the Arduino that will be used to control the robot consume current. That's because why we need a powerful power supply. We decided to use a 12 volts and a 5 amperes power source. Connection diagrams. For the connection diagrams, we make a connection in a simulate application. As you can see there, we connect the stepper motors with their drivers, and each pin of the drivers to the Admega 1 for the Arduino Uno. and we had two stepper motors, one for the gripper and another one for the base.
Now for the forward kinematics, the configuration of the robot along with the frames is the one in the image. We can see there that there's the rotational joint and two prismatic ones. With these frames, we can start the forward kinematics, and for that we must have the four variables of the Denevit-Hardenberg convention of each joint, which are shown in the screen. Then the formula of the Denevit-Hardenberg convention is the following. It is shown also in the screen, and we have to substitute those values for each joint, and we get for the joint 1, for the joint 2, and for the joint 3. Now we have to multiply all these to get the formula of the final position and rotation in terms of frame 0, which is also shown in the screen. And this is the result of the forward kinematics. Then for the inverse kinematics, to start the calculation, we decided to represent the coordinates of the end effector as xc, yc, and zz. We start looking at the architecture, which is a rotational joint at the base for direction, along with two prismatic joints for height and length. Seen from above, the distance d3 is given by the distance between the origin and the displacement of 14 centimeters. So the value of d3 is calculated with Pythagoras theorem, and the formula is given. And since h depends on xc and yc, then we have the formula to get d3, which is the third joint. Then with the distance d3, we can proceed to calculate the angle of the first joint, which is named a in the view from above. To get a, we need b and c with the relation of a equals b minus c. B depends on the coordinates xc and yc, so b is equal to arctangent of yc and xc. And we can get the angle c with the triangle formed by the third joint and the 14 centimeters displacement. And c is equal to arctangent 2 of the square root of xc squared plus yc squared minus 196 and 14. And then we just replace those values on the relation to get a, and we get the following. And the last joint is the second one, which is the prismatic one, which only depends on the value of cz. There's a displacement of 8.5 centimeters from the ground plane to the origin of frame 1, so d2 is equal to zz minus 8.5. And here's the solution with the robot for each joint. Then to calculate the Jacobian, we will use the forward kinematics position matrix. So we can calculate the linear velocity Jacobian by doing the derivative of each function of the position matrix with respect to each variable. So the formula of each cell of the Jacobian is the following. And just a reminder, the forward kinematics position matrix is shown. So applying the derivatives to each function and each variable, we get the following. And for the angular velocity Jacobian, we apply the formulas for the geometrical approach, which is zi minus 1 for rotational joints and 0 for prismatic joints. For the first joint, which is a rotational one, the value of zi minus 1 is 001 transposed, because the matrix of the frame 0 is the identity matrix. For the other two joints, the angular velocity Jacobian is just 0 because those are prismatic joints, so the complete angular velocity Jacobian is shown in the screen. And the complete Jacobian is also shown in the screen. To get singularities, we equalize the determinant of the linear velocity Jacobian to 0 and interpret the result. So we start by doing the determinant of the Jacobian, and we just factorize and cancel some terms, and we get that we have a singularity when the third joint equals 0. What this means is that the rotational joint won't be able to produce movement in an axis when it is parallel to another axis. For example, the joint is pointing to positive x, and it cannot produce motion in the y-axis, and the other way around. But this only applies on the world frame. And now we can see the interface that we will use to control the robot. It includes forward kinematics position, inverse kinematics position, and the results. We have the linear velocity, angular velocity, and the kinematics of the forward kinematics.
Se va uno por uno. That's your interface, as you can see there. We can put there the joints positions that we want to move. For example, we can put there a 4 for the first joint. We can put there, for example, 2 for the second joint. And we can put there 116 for the third joint, that is the rotational joint. The interface communicated through serial ports with Arduino Uno, and that's the way how the robots communicate. We click on the start button and send the signal to the Arduino and start move. As you can see there, first move to joint number 1, second move to joint number 2, and finally to rotation joint.